So, for thousands of years, humans have been obsessed with getting different places as efficiently as they possibly can. I mean, think about it. If you wanted to get from point A to point B, at first, the only option was to, well, walk. And then someone had the ingenious idea of getting a spinning disc, a rod, and then a cart made of wood, all putting it together and then creating the horse and buggy as we know it today. And then people started thinking that, wait, if anyone can pull this cart, why do we need a horse? And so the modern car was born. Fast forward another 100 years, and we've managed to take what was once a horse and buggy to a box of metal that can take you virtually anywhere with the click of a button. How did we get from moving our puny feet, one after the other, to a self-driving car? Well, unfortunately, we haven't, at least not in the way that makes a difference. For about a decade now, companies have been promising this revolution in transportation. First, we predicted that we'd all have self-driving cars by 2012, then 2015, 2018, 2020, all of which just remained unfulfilled promises. So the question is, what went wrong? What seems to be the problem? What specifically makes autonomous vehicles so difficult that it takes decades to get it to work right? See, the problem isn't actually building the car. The problem is the approach that we're taking to solve it. Right now, these cars are way too expensive to be bringing to market. In fact, Waymo's fleet of sensor-equipped cars cost $200,000 each, which is around 4 times the cost of any other regular car on the market right now. And building these cars is time consuming as well. You need to put on sensors, collect data, get all of the various bits and bobs to talk to each other, and obviously deal with government regulations. And finally, the solutions that we have today are just too specific for such a general problem. Before a self-driving car can actually come to our neighborhood, all of the streets, stop signs, parking spots, and dozens of other things need to be mapped, trained on, and tested. No wonder that it takes so long to build these autonomous vehicles. So, how do we go from decades to the span of a couple of years? The answer lies in a little something called behavioral cloning. Think about it this way. Rather than using LiDAR, radar, video, GPS, lasers, and dozens of other sensors on a self-driving car, we can just get the AI to watch us drive. All it needs to do is observe what we naturally do and associate our steering movements and brake patterns with driving until eventually, after some processing and training, it understands what it means to have different steering angles, speed, etc. But there's still one glaring question: how? And the answer to this question is that of a CNN. As we know here is that it will take information from images from the right, left, and the center of the car and transform them into a steering angle. And as part of my replicate, that's exactly what I had to do. And not only does this make it more efficient, it also manages to reduce developmental costs and the time to market, not to mention improving accuracy and reliability, because now the AI can actually pick up on trends that we might not have even noticed. So let's go back to the original question: how? And once again, the convolutional neural network comes to our rescue. We have three separate images, the right, center, and the left, that will each get fed into this network and output a steering angle. And these images are taken from both the sides of the car and the front of the car inside Udacity's self-driving car simulator, since you really don't want to be taking an actual car and doing this if you don't know what you're doing. So here's an example image: the left, right, and the center. And these images are going to be 320 by 160 pixels, which are then going to be fed through a series of 4 convolutional layers, which take the input, scan it, and then will apply different filters in order to detect different parts of the image. Now, one part of the network might detect lanes, the other edges, the other the curve of the road itself, and maybe even future turns the car might make. Think of this part like your eyes scanning the slides right now from left to right. Then the output is going to be flattened into a one-dimensional vector and sent through the brain of the neural network. Now, this is the part where most of the processing happens, taking in the raw pixel values and drawing associations between them. And the output of all of this is one single number: the steering angle. Now, all we need to do is get our model to talk to the car. And we're going to be using a server-client model to get this to happen. In this case, the server is our model, and the client is the car. So the car is going to be taking screenshots and sending us the right, center, and left images. Then our model is going to take those images, resize them, and then run the network on top of it to produce one single number, which is the steering angle. And boom, We've just made a basic autonomous vehicle that is responsive in instantaneous time. This entire cycle takes around 1 second to occur and happens nearly instantaneously so that the car can react to real-time situations. Now, in reality, we have a much tougher road ahead of us. Making a self-driving car might be easier with behavioral cloning, but it's still a far cry from easy and simple. What matters most, however, is that we're one step closer. We're one step closer to a future where 1.9 million people don't have to die because of simple human mistakes. A future where people don't need to pay the ultimate price just because of some careless driver or just improper regulations. What matters most isn't how much further we can push this technology, who's working on it, or how it's being developed, but rather what we choose to do with it. Thank you.